Hello everyone, my name is Weizhen, a graduate student at Wuhan University of Technology. The paper I present is an efficient message dissemination scheme for cooperative driving via multi-agent hierarchical attention reinforcement learning. Cooperative driving systems have been verified to improve road safety, traffic efficiency, and environmental sustainability. As a networked control system, vehicle control in cooperative driving systems relies on the periodical exchange of information via B2B communication. Thus, it is critical to design an efficient message dissemination scheme for cooperative driving to periodically broadcast beacons. A general scenario with various types of cooperative driving applications will coexist on roads in the foreseeable future. Some studies have focused on the design of message dissemination protocols for cooperative driving systems, using a synchronized mechanism to avoid intra-platoon contention, but few of them have considered the realistic multi-platoon traffic scenario. Besides, rule-based inter-platoon coordination mechanism like token-based methods requires significant communication overhead in exchange for collision reduction. Moreover, the message dissemination under such a hybrid traffic scenario includes beacons from cooperative drivings and safety messages from individual drivings. Most of the existing researches are designed for a simple or specific traffic scenario, ignoring the impact of the complex communication environment and hybrid traffic scenarios. In this paper, we propose a novel reinforcement learning-based scheme that could efficiently learn the various communication scenarios' hidden patterns. We formulate the decision-making process of cooperative driving as a Markov game. Each cooperative driving is defined as an agent. An agent's observation consists of its mobility and the slot occupation information. At every time step, each agent takes an action that indicates whether it keeps silent or chooses one slot to send a beacon. The reward of each agent depends on the number of beacons that have successfully been delivered and the transmission power consumption. Notice that the beacon reception information is informed by other cooperative drivings in the same platoon. Such a task gives rise to challenges in the following aspects. Firstly, transmission collisions are inevitable in a highly dynamic environment, and such collisions will cause the delay-reward challenge. Secondly, in vehicular networks, the exposed terminal and the hidden terminal problems are leading causes of transmission collisions. Thus, integrating the mutual influences among agents into the decision-making process becomes essential. To address the challenges, we propose a novel reinforcement learning-based framework named MAHA that integrates hierarchical framework with graph attention network. The MAHA framework is detailed in this figure. Each agent adopts a hierarchical framework consisting of a manager module and a worker module. The manager operates at a lower temporal resolution and is empowered to set goals for the worker and reward the worker for following the goals. We adopt the transition policy gradient method to train the manager's actor. The worker operates at a higher temporal resolution and outputs the action. The worker's actor is trained via both the intrinsic reward set by the manager and the extrinsic reward obtained from the environment. Besides, we integrate each of two hierarchical levels separately with graph attention network to specify different weights to different agents within a neighborhood. Since the manager and the worker operate at different temporal resolutions, the definitions on the neighborhood used in the two levels are different. Furthermore, in order to ease the training process, we employ an A2C framework for the manager and adopt a DDPG framework for the worker. The overall training algorithm of MAHA is presented here. To evaluate the performance of the proposed MAHA framework, we consider hybrid traffic scenarios with and without rule-based cooperative drivings. We also consider scenarios with different safety message generation distribution and different traffic flow generation distributions. As shown in the figures and the table, the proposed MAHA framework can achieve the best performance among all methods. Unlike the rule-based methods that choose the time slot based on certain regulations, the MAHA framework can lead the agents to learn the safety message distributions hidden in the environment. Thus, the agent can easily choose the slots that have the lowest collision probability. The right top figure shows a visualization of the policy driven by MAHA. Overall, the agent chooses the third and the 53rd slot to send a beacon, which has a low probability of colliding with safety messages. Besides, when a rule-based platoon joins into the scenario, the agent changes the slot usage depends on its observation. In conclusion, we proposed a reinforcement learning-based framework for beacon scheduling in cooperative drivings, which could efficiently learn the hidden traffic and communication patterns in various vehicular communication scenarios. Then, we propose a novel MAHA framework that can overcome the delayed reward challenge and handle the mutual influence among agents. Furthermore, we evaluate the MAHA framework on various scenarios consisting of both cooperative drivings and individual drivings. The MAHA framework can improve the beacon performance in all scenarios. That's the end of my talk. Thank you very much for your attention.